Welcome. Today we're going to have a little bit of a chat about Clojure 1.11 Alpha 4, and I have some esteemed guests with me. I'm Alex Miller. I've been working on the Clojure team since 2013. So, Ghadi, why don't you introduce yourself?
My name's Ghadi Shayban. I've been working with Clojure and a super fan for about 10 years now, and I'm a senior staff engineer at Nubank.
And Fogus.
Yeah, my name is Michael Fogus. I have been using Clojure from the very early days when Rich was hanging out on IRC and answering questions for 4 people. And I work with Alex on the Clojure core team, and I'm excited to talk about this.
So yeah, this is the first time we've done anything like this. We don't really know what we're doing, so this is a bit of an experiment. So sorry if it's filled with errors and brokenness, but we'll try to do our best. So my plan today was just to walk through each of the JIRAs that's included in the Alpha 4 release, which came out yesterday, yesterday, and just talk about them a little bit. And Fogus and I have worked on all of these at some point or another, in some cases patches, in some cases screening. And I included Ghadi in particular because he has worked on some of the patches and was the inspiration for at least 1 or 2 of the things that are included here as well, even though his name might not be on the patch. So I thought he would have some interesting things to add for that. So this first ticket is 2673, and this was let me open this up and we'll switch over to this. This actually started as this ticket kind of migrated, and sometimes this happens as we work on things, and there'll end up being a cluster of tickets which kind of change in how they what part of the problem they're representing. So when this ticket started, it was because there were 4 methods in the new Clojure, at the time, clojure.java.browse namespace that was added in 1.11 Alpha 3 that had reflection in the method bodies. And that was just oversight on my part. I wrote the patch for that originally. And so the 4 methods there that were included were abs, min, max, and scalb. And the as we looked at it further, I had some second thoughts about including abs in the math namespace, because it actually supports, but it has implementations for both long and double, and both of those are useful. And it has other types. It had other types that we didn't care about, things like int and float. It didn't have support for big integer, big decimal, or obviously ratio, because that's a Clojure type. So as we started to look at it more, we ultimately decided that it was worth giving it the full polymorphic number treatment that all the other math operations have in Clojure core. And it's worth it because it is probably the most frequently used function out of that math library. It's frequently needed. A lot of times I will go out and look under in GitHub. I use grep.app a lot to go search GitHub to find usages of things, and abs is certainly frequently called. And so, and there are a lot of implementations of it out there. Most of them are pretty slow in terms of what they do, and or limited in terms of the types they support. So it was one of these functions that seemed like it deserved a little bit more attention, and it was worth the full polymorphic treatment to get it for all the types. So we moved it into clojure.core and removed it from the math namespace. Min and max, when I started looking at them closer, we of course have min and max in Clojure core. and we actually have them implemented as varargs. And so the min and max that are in math, Java line math, which I could probably open that. Max, right? So if you look at math.max, there are a bunch of different implementations for different type combinations, but they're all just for 2 numbers. And so the version that we have in Clojure. So Clojure max is implemented as a multi-arity thing, which is backed ultimately by a two arity. The actual implementation, if you look at the sources, is really in the 2 arity version. So again, we decided it did not make sense to leave these in math. We have implementations that are more powerful in that they're polymorphic on all Clojure types and varargs in Clojure core already. But what was useful was to go and replace the min and max versions for the types that math.max supports to use the versions that are in math and Java line math instead of the implementations that we had. So it helps to look at the patch change for that. Yeah, so for example, max long would say if x greater than y, return x, else return y. Now it just says math.max. And that's useful because these functions in Java line math, some of them are backed by hotspot intrinsics in the Java implementation that actually compile down to assembly. So this is potentially a much faster implementation depending on the Java version and other things. So we did that for a few cases. And then let's see. And then ScalB has a reflection thing. We ended up actually folding that into another ticket, which I will talk about later. I think those are the changes there. You guys have anything to add to this?
I think that not until we get into the other ticket, I think is interesting conversation to come out there.
I don't know if it's interesting to talk about how Clojure supports polymorphic functions like that. I don't know how deeply we want to go into the weeds on that, but it's moderately interesting. Close all these. Core here. What were we talking about? We're talking about adds, right? So this is the version that's actually in. If I'm looking here at the current alpha4 source, so if it can inline, it does with a call to numbers. So anytime you have an inline function, in general, if this can be called if you're making a call that's something like abs5, that's a case where it's going to inline. But if you're using it as a higher order function, typically you can't inline, and then the actual method body will be called instead. But they're both routing to numbers abs. That is something that takes, well, it's overloaded. So if it's a long or a double primitive, then those immediately route to math.abs. That's the new function we're trying to expose out there. If it's an object, then it routes through this ops call, which selects one of these ops classes over here and calls the appropriate method on it. So if it's a long object, for example, it'll end up calling this longops.abs. which coerces the number into a long primitive, calls math adds, and then boxes it back into an object on the other side. And this is kind of the way all the polymorphic number stuff works. So we're trying to cover the primitive cases quickly. So these are the ones that, like, if you align your code so that you have primitives in it, you're going to end up doing these fast paths. But any other thing that you do will route through the ops classes and then call the appropriate method. So, all right, so that's that one. And the second one we have is the iteration generator function. Ghadi, I'm gonna let you talk about that one.
Sure. This ticket had a long life cycle had a preceding ticket. I think it was CLJ-1906 that proposed using a different implementation. But the essential problem here is that there's a variety of different flavors of iteration APIs that programmers encounter and need to consume. And all of those iteration APIs have to expose three main operations: some way of getting a value, some way of moving to the next value, and then a way of seeing, are you done? And so some of those API providers combine the get the thing operation with the move operation. So like Java iterators here, they have a separate done operation called has next, but the move and the get are bundled together. When you call next, you're actually moving and you're getting at the same time. So on the other hand, there's like .NET's IEnumerator interface. They combine move and done, but they have a separated get operation. So then there's wire APIs. So if you look at a lot of Amazon APIs like S3 list bucket operation, those generally bundle all three ops together. They have get, move, and done. You just call the API and it returns you some payload with possibly some values and a way of moving to the next thing and a signal if it's done. So those wire APIs generally bundle all three together. Clojure seeks, that's an iteration API, and that separates all three operations. The main problem here is that you're not in charge of how those API authors have bundled the three operations together. So Clojure core iteration is a new function that allows you to extract a series of values from some sort of iteration protocol. I don't mean like a Clojure protocol, I just mean some method of calling an API, some iteration protocol that you did not write, okay? And so it offers you a bunch of different knobs and into customizing those operations of get, move, and done. So where to start with this? So you need to be able to like launch this process of consuming the iterated API. And so the main thing to consume is this idea called step, and step is presumed to be a stateful function. The docstring's a bit of a mouthful. Might take a whack at clarifying it a little bit, but the step function takes, it says, some opaque continuation data K. Let me translate that into English. It takes some sort of continuation token. If you're thinking about the S3 list objects API, when you get a payload of results, embedded in the result is a way to take a key, like they usually call it like next token or continue with, or some sort of opaque identifier, and you should be able to feed that back into the API to get the next body of results. And so that's what this opaque continuation data K is. So just think of it as a continuation token. But at the beginning of the process, you don't have a continuation token. So you're going to take that token's going to be nil at the beginning. So all right, so you call step on this continuation token and you get a thing, and the docstring calls it an opaque ret. Ret is the main stateful thing that's carried through this whole iteration protocol. And so Given a ret, you have a way of getting the value inside the ret. And that's called VF. You call the value function on ret, and it gives you the value. And so if you had a page of results from S3, calling VF would extract the actual listings. There might be an envelope around the listings, and that might represent your ret. But so VF will give you the values. There's a sum function to say, hey, I'm looking at this page of results. Is there anything there? And so that kind of doubles as the done function in the get move done trio. And then you have a way of moving from the page of results to the next page of results. And so you need to be able to extract the next key for the next call to step. So it's probably easier to just look at an example because that's a lot going on here. So Alex, I'm wondering if you could pull up that log groups example and maybe embiggen it. All right. Okay, so iteration, the very first argument it takes is that step function. It's some sort of side effect thing. And so here it's invoking an Amazon client with an argument, and that argument is the request. And so you can see there's a cond, and by default, the request is going to say, describe all the log groups. And if we have a token, we're going to actually add that to the request and say, but on the very first call to step, you're not going to have a token. So it's just going to say describe log groups, and it's going to return you the very first page of log groups. So usually there's a different pattern when you're launching this process of iterating through an API versus subsequent calls from the very first call. So so this is going to be a common pattern here. You have some step, takes a token, and the token will be nil at the beginning. So you can just ignore it and provide whatever the base request is. And then you see there are two other keyword arguments, the KF, the key function, which gives you the key to seed the next call to step. And that's this next token. I'm just using a keyword as a function there. And then there's the value function to extract the value from the return of a step. And so when you call the AWS describe log groups API, it provides you a bunch of metadata about the answer, but embedded in that map is the actual log groups that you're trying to enumerate. And so we're going to extract those with log groups, and we're going to feed those log groups and cat them into a vector. You'll notice in the docstring of iteration, it says it creates a seekable or a reducible. And all that means is that you can consume this thing, you can consume the result of iteration, as in the values produced by this iteration protocol. You can consume it with any of the reduce flavor operations like reduce, transduce, into, and it'll do that efficiently. So like the call on the screen just builds a vector directly from the answer. It doesn't have any intermediate results there. But you can also consume it as a seekable, and if you call seek on the result of iteration, then you get something that's cached, and you can consume it lazily, or however you typically consume a seek. So yeah, it's kind of an elaborate function.
That would be kind of a dangerous seek, right? In this case,
it would what?
A seek that's lazily going out and hitting the internet, right?
It's true. I think most cases will use the reduce side of the fence, especially since there are side effects happening. So, but yeah, it gives you the option in case you want to use it as a seek. But there's a lot going on in this docstring. You can provide different ways of saying, is there a value here? Extract that value, get the key to produce the next iteration step. And then there's also, you can override what the initial value for the initial key But yeah, so this is just a way of consuming a bunch of different iteration APIs that may be bundled in different ways. And this should be general enough to encompass all the things that you'd see in the wild.
So I think other additional work on top of this sounds like maybe improving the docstring a little bit would help. And Ghadi, I'm hopeful that you'll write a blog post with some more examples. I think probably an iterator example would be good, just because people are familiar with that one and things like that. And then there's also a core async version of this.
Oh yeah.
That I don't have handy, but and I have a to-do to make a ticket out of it, which I will probably do on Monday.
So the core async one's going to be really cool because usually when you consume one of these APIs, you if you're doing it in a non-concurrent way, you're going to fetch some results, process the results, and then you're going to go ask that API, fetch me some more results. But as you're processing the first set of results, it could be fetching in the background, right? You could pipeline this, the consumption and the fetching. And that's exactly what the core async version will do. It has a knob on how much run ahead it'll do fetching successive pages. So the consumption and the production of those results are concurrent in the core async version. And it's like 10 lines of code. It's really quite nice.
So like I could use that in tools deps. If currently we use the S3, we don't have support for the streaming API, but we could pipeline the streaming and consumption of the downloaded jars from S3 or something like that if we wanted to.
Sure.
Yeah, should be cool. All right, well, that's cool. Did you, I wasn't in I know you had a long conversation with Rich probably a couple years ago now about this function. Were there other names that were considered, or I know that's always a fun game.
I had different ones on some previous versions. I think Rich just used iteration directly, but I think I had productions in one version and then series in another one. But of course, there's a lot of similarities here with schemes unfold, and so it'd be interesting to compare and contrast those two. I think this one's more general. So.
Cool. That's a cool new thing. And I think it's probably it's one of those more advanced things, but certainly something that I've run into any number of times. I see people ask for it probably once a month on Clojurians. They don't know what they're asking for, but it's this problem. This is the solution to the problem they have. So I think if we can get better at our storytelling about when it's useful to use this and how you can use it, I think it could be pretty useful to people.
Sure.
All right, on to 2621. Oh yeah, this one was filed by Alexander Yakshev, who does a lot of the Clojure Goes Fast stuff. And so it's kind of, and I was actually going to show some bytecode for this one. So probably easier to show in the code than it is otherwise. So in an example like this, this is a case where we're getting an atomic long object and calling increment and get. And you'll see that increment and get returns a primitive long. But in this particular method, which is just here as an example, we're actually returning nothing. So we've got a nil return, which means that the return value of this call, this method invocation, is unused. And so the problem being identified here is that the Clojure compiler is doing work even though it doesn't need to. So I have this set up to be able to compile here. So I have a very little Clojure build script that does creates a class directory, creates a basis from the current dependencies, deletes the target directory, and then compiles all the Clojure source here into target classes. And actually, that's not going to work because this is using things that doesn't exist. So let me make that work. All right, and that's okay. It's the other example I was going to show. And then if you want to use, so Java includes this thing called Java P, which lets you disassemble Java class files and look at the contents. And so I've set up a call to this here. And this is not the right one. Something like this. So -c says to show all the stuff. -class path, I'm adding the classes directory that I just compiled, and then just pulling in the clojure, the class path for this project. And then you have to give it the Java class name in your class path. So if I go out here and oops, that classes, you'll see there's a box red /$ink atomic, which is this function. So look at some bytecode here. So a typical clojure function gets compiled into a Java class. So that's what we're seeing here. And you'll see several invoke methods. So see invoke static, invoke, those are the only two you'll have in this one. Invoke is a generic entry point for a case where we don't, it's sort of so this is the direct interface. This is the indirect interface. It's probably the best way to say it. And the indirect interface just calls the direct one. So this is nothing more than a call to invoke static. So the real guts are always in invoke static. That's the place to look. And for this function above, you can see that it loads L and then throws it away. That's locals clearing. And then casts the input to an atomic long, calls increment and get. So that's our actual call here. And then you see this line here, which is a boxing call. It's taking the output of increment and get, which is a long, which in Java class speak is a J. That's a primitive long, and is returning a number, an object, which is a number. So there's some code in the compiler that is automatically boxing the return type of increment and get. And that in this case, this call here is totally useless. It's not doing any useful work to us. It's just slowing down our program. And you can see that because the result of this is the number, which immediately gets popped and thrown away. And then we load null and return it. So there's no reason to do that stuff. In some cases, Hotspot will be able to clean that up for you, but Alexander indicated that he was actually seeing this as in some performance profiling he was doing. He was actually seeing this show up as work that was slowing them down. So it's definitely a case where Hotspot was not cleaning them up. So the change, I don't know if it's useful to look at the change or not. Maybe I grabbed the. We look at this code is. Not sure if I'm in the right. Let's see right now. I'll just have to edit out all my fumbling of looking for source code. Where are we at? 15 So I'm not in the right place. So the big thing here, the change is basically to do do this right here. If the context is a statement context, not an expression context, then there are several cases here. If the return type is long or double, we actually need to do a pop2, and that's because longs and doubles hold 2 slots. Objects and all the other primitive types hold 1 slot in JVM memory places, so it needs to do a pop2. If it's void, then we didn't get anything back, and so we don't need to do anything. But if it's not void, then we need to pop 1. So this code I lifted directly from the exact same situation for static methods, which has this exact same code is almost identical to all this. This part of the code was different, so I went and well, Alexander's patch had gotten pretty close, and I made it a little bit closer by taking exactly the code from static method expression. So feel a little better. It's obviously code that's been run a lot. I think that's basically the change there. So I guess I could show the after if you're really curious. I switched to Deps Eden. There are other ways I could do this, but this is probably the most expedient. File alpha4. It would be most expedient, except I have code that depends on alpha3. So you should now see that we do the increment and get, and then there's an immediate pop2. So there's no boxing or anything like that. So less work, go faster. All right. Our next is CLJ-2663, and I'm going to throw this one to Fogus because he spent the most time on this one.
Yeah, so the basic idea is that if you have a vector in hand and you wish to compare an equivalency with another seek, then it executes some code in a class called a persistent vector, and that code does a couple of things. The first thing that it does is that it calls a size, the size method on the operand, and a count on the vector. And the idea is to try to bail out of the equivalency check early in the case where the two sizes don't match up. So what the problem that was arising is that if you have a vector and you wish to do an equivalency check against an infinite seek, then calling a size on an infinite seek is a problem. It'll never terminate. So we looked at the problem that the size was being called without a guard, and determined that that size can't be called in every instance. There's only certain cases where you can call that, and one is that well, the case that you want to throw out is if the operand given doesn't respond to a size call, and you can do that by checking against whether it implements an persistent collection interface, or if it has a count method, if it's an instance of counted. So I added a little bit of a guard in there on the call to size that does some Boolean logic, which interestingly, I haven't had to think about operator precedence in a long time. And so the combination of instance of calls and ors and ands was an exercise in retrieving some long lost Java information. But now we have a guard on that call so that size is not called in the case where in a problematic case, such as an infinite seek and some and probably what lazy seek, I suppose. And instead it'll fall through and it'll iterate through the vector and the operand seek and then compare the items and bail out if something doesn't match, or it will return true or false based on whether or not the operand seek has more elements in it or not. Interestingly, we determined that this short circuit logic for checking sizes was probably was adding a benefit that we weren't taking advantage of in the case where generic seek equivalency checks were being done, which is in a class called aseek. And in aseek, it was always just falling through to a one-for-one element comparison. But I added a little bit of logic here to check that if both objects have a count, adhere to the counted interface, go ahead and check the counts and bail out early if if the sizes don't match. So this is an added piece of code that now everyone's going to get. We'll see what happens with that. When doing a check like this, checking the count in the beginning, it benefits you obviously if this count bails you out faster than doing one-for-one checks would do. However, it might not help you if the first item in those sequences are different, right? You've now walked both sequences, counted them, and compared the count. If they happen to be the same size, then it's going to then do a one-for-one comparison. If the first thing is different, then it's going to bail out. So it might have been better just to do a one-for-one comparison in the first place. However, I just suspect that that's most of the kinds of things that we're going to be comparing are probably will have some concatenations on the ends, and so I think that this early bailout is going to help us a lot in most cases.
I thought the interesting, tricky bit about the vector change was that there are really three partitions. So it's a quiv in a vector. So we know that one of the things is a vector. And the question is, what is the other thing? And so if it's a vector, we do something fast. But there are sort of three partitions after that. And one is, it's something that it's a clojure collection that is counted. And so counted is a marker interface in Clojure that indicates that you can call count on it and get an answer in constant time.
Mm-hmm.
So usually it's any of the concrete collections and can be some other things other than that as well. In that case, you definitely want to do the count check, right? And then we actually support comparison with Java collections as well.
Yeah.
So you might have something that's like an array list. And in general, we assume that Java collections that are not Clojure collections also are finite and can tell us the answer in constant time. And so in that case, you definitely want to use size to check. But there's a weird middle ground where you have something that is a Java collection because all clojure collections are Java collections. It is a clojure collection, but it is not countably, not countable in constant time. So things like, like a take on a range or something like that, or take on a cycle, something that's finite, not infinite, but it is a clojure collection. And in that case, we want to avoid checking and then instead walk through them one by one until if one of them ends early, then you know that they're not the same, right?
Yeah,
So,
exactly right. And I mentioned that this was an occasion for me to break out the operator precedence table, but it also was an instance where I could go back and draw up a truth table as well, because if we think about what the guard logic is that we're checking against whether it adheres to iPersistent collection or and also the counted interface. And so where we want, it turned out the truth table turned out to point to logical implication such that we wanted one case where it didn't, you couldn't call size on it, and that's where we knew that it wasn't going to adhere to iPersistent collection, and it wouldn't be a Java interface. We knew that it could potentially be a Java interface because in that partition you mentioned, where this logic was happening in the case where we knew that the operand was going to be an instance of list, and calling size on an iPersistent collection meant that if it was counted, it would be backed up by count, and we know that those instance of lists has to have the size method as well. So it was. I went back to my computer science 101 knowledge that I haven't used.
You almost had to break out de Morgan's law there.
Yeah. Yeah, I had to, there's no implications operator for Java, so I had to turn it into a not or instead.
Good stuff. That ended up being a small change, but it was fun to think through.
Yeah, it was interestingly challenging, and I enjoyed this fix. Don't always enjoy them all, but this one was a fun one.
All right, so the next one is this problem with hash collisions.
Yeah, this is another one that
Yeah, I'll let you take this one too.
Yeah, so I didn't discover this. Paula Giron found this and posted a question on Ask Clojure and pointed out that in the case where you're using raw symbols for your dispatch keys in a case statement, you can run into an instance where two things may hash to the same value. And when that happens, you were having problems looking up the symbols because, well, mechanically, this case, the case macro is backed up by a clojure special form called case star. And what case star does is it checks the dispatch keys on the left-hand side of the case doubles, and it builds a dispatch table, which is then passed into the case special form, and it calculates what's actually, which branch is going to actually be called. But what the case star special form doesn't evaluate any of the dispatch keys. But in the instance where the case macro detects that there's a hash collision, it builds something else out of what is it? It builds it out of a cond p. It builds a cond p, which uses the equal sign, the equals function, to in those hash branches. And so, unfortunately, cond p does evaluate will try to attempt to evaluate those hash keys. And in the case where you were using a raw symbol, it attempts to now it tries to resolve that symbol to a local. And if you happen to have that thing bound, then your behavior is going to be who knows what's going to happen. But if it's not bound, then
Becomes unexpectedly anaphoric at that point, right?
yeah, all bets are open. All bets are on the table. But in most cases, it was probably going to give you an error, and in that it can't resolve that symbol. So what Paula identified is that in that hash collision branch, when building the conp, you can quote those dispatch keys, which become the left-hand side of the conp checks, and then now you don't run into that problem anymore. And it's not. This is really small instance. This is a small change, and I think that it has a small footprint in the way that in the generated code, because it only ever happens in the case of hash collisions, which don't happen that often, which is probably why this went a long time without ever being really noticed. And it interestingly, it fixes the contract of what case is saying, in that those dispatch keys should be compile time literals, which technically symbols are. And so I think it was a really nice, elegant change. That was interestingly her first patch to Clojure ever, which blew my mind, because Paula has done so much for the Clojure community, and now she has a patch in Clojure, and I'm happy to have helped.
Would not have guessed that was her.
Yeah, me neither.
So
a million years.
I'm glad it got through. That's good. All right, cool. So that's that one. Next one is 2670. And this one, this came from you, your offhand comment from you, Ghadi, I think, if I remember correctly.
Yeah. I didn't do any of the work for this. I just kind of
You just made it a side comment on Slack, and I took it from there.
threw it over the fence.
Yeah. So yeah, the big thing here is that a lot of these, so math has these methods. I still have this. Yeah. So if you look at something like multiply-exact, multiply-exact is, so there's really, backing up even further, there's three kinds of arithmetic operations in Clojure. There's three families. There's the normal family, which are things like plus, minus, times, whatever. And then there's the plus tick mark, which is the promoting family. And there's a plus tick mark, times tick mark, etc. And then there's unchecked add and unchecked multiply and things like that. And so those differ in that the first category is non-promoting. The normal math operations are non-promoting, but they are checked for overflow. So that's the default in Clojure. If you want promoting, then you use the ticked forms. And if you want unchecked, non-promoting but unchecked, which is generally the fastest case, you use the unchecked. You either use the unchecked operations, or you can set the unchecked math dynamic var to true. And so, so that unchecked case is the fastest case, but the default case gives you is almost that fast, but gives you more safety in that it will throw in the cases of overflow, underflow, things like that. So in Java 8, I believe, yeah, it says right here. In Java 8, they added these multiply, increment, all these exact forms in Java Lang math. And they basically have the same semantics as Clojure's default checked unpromoting math operations. But the big difference is, and this is what Ghadi mentioned, is that these things are built into the JDK as hotspot intrinsics as of Java 8, I believe. And then they've changed a little bit over the years. There's additional things that have been added, but these actually are basically in the JVM or in the JDK, I guess, in the compiler. It's in the compiler. Where are the whichever of those you call it, it will replace the compilation of these things with, you know, handcrafted assembly that does fast things that know what to do. So it will depend a little bit on what chip you're on and all that sort of what JDK you're on, exactly what will happen in these cases. But they are potentially faster alternatives than the for this semantics than what we were doing before. So this patch just basically replaces these calls inside the Clojure numbers implementation to use math.exact when they can. And those are mostly arithmetic operations that all happen to match all the ones that we already support. And then to_int_exact is kind of an interesting one, which is when you convert from long down to int, when you downcast, which we do actually have a method specifically. If you use the int coercion method on a primitive long, you'll end up falling into this category. And so that is actually an operation that we have inside the inside Clojure's implementation. So I replaced that one too. So if you look at the patch, it is mostly going into things like add on long, and you can see that this was an implementation that would is basically x plus y, but it also has code in there to check for overflow. And so that's replaced with a call to math.add_exact, which has exactly the same semantics in that it throws, and except that it's presumably faster on when that can be implemented that way. And I was able to manage to get some performance information, but it is really tricky to manage to detect changes that are at this level in performance things without having hotspot get smarter than you and start to do other things. And so I did not find the results believable in some cases. So I think hotspot was outsmarting me, especially once I got to like Java 17. So I looked at it on Java 8, 11, and 17. And I actually think I saw the biggest differences on 11. And it seems like a lot of things had gotten better in 17. So
yeah, they were being calculated before you hit the enter key, right?
Practically, yes. I'll find the int cast. Yeah, so here's long to int cast. One very small change here is that this threw illegal argument exception before, and it will now throw arithmetic exception, which are both Java runtime exceptions. This is actually a change in behavior in Clojure. So that's something it's hard for me to imagine that this is something that somebody is actually checking for and doing something at that fine-grained level. But if that does pop up, we'll maybe reconsider this one. But we welcome your feedback. Trying that. So that was a fun one. 2680. Oh yeah, so this was kind of a side quest while we were working on the other reflective inlining changes for math, and Rich came up with this example. This is a case where we have a primitive local. So when you use a let in Clojure, and you use a number like this, it Clojure will understand that this is a primitive double, and X is a local that will be bound to that primitive double. So this is a case where X is being type hinted as being a primitive double. So those two things match. But if you do this in alpha4 or anything earlier, it will actually throw and say you can't type in a primitive local, which is just a blanket statement that the compiler says if you both have a primitive local and you type in it, then it's bad. So we made that check more nuanced to say if you have both of those things and they're different, then that's an error. But if they're the same, we'll let that go through. We thought this was going to be an important little lemma to do for some stuff we were doing with the reflection stuff, but we ended up not actually making use of it. But we changed that anyways. So,
yeah, I think this is an interesting example of opening up new functionality, so to speak, in a branch that was illegal before.
right.
We've found Clojure features in those kinds of instances where we made something possible that was previously impossible.
Yep, exactly. So this is an example of that. So shouldn't bother anybody. Anybody who had it before, it would have been an error, but now it's not. So let that flow through. 20. Oh yeah, this one. So let's get that there. So this is one that came up in Ask Clojure, and I ended up spending like a whole day on this one because, and there were some patches on it and things like that. And I kind of just started over with it because the problems were deeper than previously identified. So it really was kind of fascinating, and I don't know if I can get to a point where I'm trying to think if there's something I could show that would make this obvious, but the problem that you see as described is that if we can have both a global hierarchy for multi-methods, and you can also create local hierarchies that are used for a specific multi-method. This is not something that's actually used particularly commonly. So you say def multi local, and then you can actually pass it this option to pass a specific local hierarchy. And so the symptom that was being observed is that preferences only looked at the global hierarchy, not the local hierarchy. So that was the symptom. The real problem is that a lot of the code, there were several strategies being used to manage the multi-method state inside the method impls stuff. And it's complicated because there's some caching that goes on, and that caching has grown more complex over time, in particular to deal with the case of defaults. And can't remember now if this actually ended up getting in, but for negative caching of values that don't exist. I think we didn't end up putting that in, but so, and then there's a locking strategy used to manage some of that state. And there's a preference table, which is separate. And then there's a spin check that's done at one point where it basically grabs the state, tries to manipulate it, and then will, if the state hasn't changed while it did that, it will replace it. And if it has changed, it just cycles and tries again. And this kind of is taken into account that multi-methods, the reason state changes in a multi-method is that you add a new method, or you add a new preference from one type to another type, or one value to another value. But those are things that are done as we load code. They aren't typically done concurrently in most cases. So the vast majority of the time, it's a single thread that's doing this work. So it's sort of optimized with that assumption in mind. But it's really a mess. When I started looking at the code, I'm like, it's not, it's just one of those things where it has grown over time. The people have put optimizations on it over time, and it's gained state and all this kind of stuff. And so there are these three internal private methods, prefers, is, and dominates, that all touched the state in different ways. And some of them didn't follow the same protocols that everybody else was using. And so the first change I made was to make all of those things get past the hierarchy to work on. So those three methods became stateless. You gave them the thing and said, okay, do your work on this hierarchy. And so that is just, that's always a good move, right?
And by that, Alex, you mean that in the case where it was using the global, it was given the global.
Right.
Okay.
So it doesn't touch any of the state. None of those three methods, which all do logic, touch any of the method that's in the multi-method impulse at all. They are given the hierarchy to work on, or whatever other state they need. And then I went through and did some additional work to clean up how the state is given to those methods and things like that. And I don't go through all the details of it. I don't remember all the details of it, but you can go look at the patch if you want to see the details. But all that stuff is now much better than it was before. And so it was one of those things where it's this tiny little rabbit hole of Clojure, you know what I mean? And I did not expect that I was going to screen this patch and spend an entire day diving down that rabbit hole and drinking various potions and eating various things to get back to my original size. But that's how I spent a day or a half day. Maybe it was a half day. So that's fun. It's better. Into completion. This is one that probably Ghadi can talk about.
Yeah. So this one I ran into when using AWS client libraries that expose anomalies as data instead of exceptions. And so there's a little known transducer named halt-when that came out a few releases ago. I can't remember. But halt-when's neat. It allows you to stop the reduction process when the input value satisfies some sort of predicate. Okay. And it has a couple knobs. It allows you to also pass a function to sort of terminate the reduction process using the intermediate value that's coming in and the input that failed that predicate that you're trying to halt on. But if you look at that first line of the example, it's not using that second knob. It's just saying halt if the input has if the input is an anomaly. All right. The issue here is that the way that the implementation of in2 was written before didn't allow you to use this transducer, and for kind of a subtle reason. But in2 is really just reduce conj, right? The transducer version of in2 is just transduce conj with the transducer. But Alex, if you can just scroll down onto the implementation of the current implementation of in2. Yeah, okay. So the current implementation of in2, it has kind of two branches. It says, do you support transients on line 4? If you do, then you're going to transduce with transients and then call persistent on it. Otherwise, we're just going to do transduce conj on line 6. But what's interesting on line 5 is that it's calling transduce, it's passing conj as the conj bang as the reduction function. It's starting with a transient, and then the transducing process finishes, and then it calls persistent to turn that transient back into a persistent data structure, and then it slaps the metadata from the original collection back on to your result. So the subtlety there is that if you pass halt-when as a transducer, what halt-when is going to see, so when you do the halt-when takes two arguments: the predicate that you want to fail on applied to the input, and then what you want to do with the intermediate value and potentially that failing input to terminate the reduction. So halt-when was actually seeing a a transient collection. Okay, so the transduce would start, halt-when would abort the transduce, then halt-when would do its logic, which is usually going to be, replacing that result value with, some whatever you want to terminate with. And then you see the implementation of int2 is going to call persistent bang on whatever halt-when returned. But whatever halt-when returned is going to be some application space thing that the developer wrote, right? It's not, the developer is not aware that it's going to be a transient in there. So the sort of correction to this is to make sure that the transducers never see uncompleted values. So you could see on line 9 of the new code, sorry, on line on line 7, the call to persistent is pushed down into the completion arity of the reduction function rather than on the outside of the call to transduce. And that makes sure that whatever's passed to halt-when is going to be a completed value with the metadata slapped back onto it. So people used to see, if you try to use halt-when with int2 previous to this fix, you would see some sort of class cast exception that said either you can't do that with a transient value. You're trying to put metadata on a transient value, or put metadata on some other value. But you're going to see some sort of class cast exception. So so now you can use int2 with halt-when, and there's no issues. So maybe this should be a call to action for people to look at halt-when and see when they can use it, because it's a neat little thing.
And Fogus, I'll commend you on your rewriting of this, cleaning it up, because I was confused by it when I first read it, and I have not. This is the first time I'm rereading it after you've worked on it, and I find it very clear now. So
yeah, well,
nicely done.
Part of getting into the headspace that required me to actually screen this was to understand it, and the process of writing this ticket was a big step in that regard. And I found, and once I understood it, I found it a very elegant solution.
Yep, it's real clear to me now why this was bad in the first place. So it's very good. Let's see. Next one is 2665, which has a lot of gory guts in it. So a new feature that was added in Clojure 1.11 alpha 2, is it alpha 2? I think it was alpha 2. Is this new as-alias support, which allows you to say that I'm going to require a namespace only as an alias, and it does not need to be loaded. And then you can use that alias, for example, in keywords and things like that. So a question that had not been thought about, but had some more thoughts about after it went out, based on some questions from some of the various tool makers out there. We're starting to look at support for it in like Condo and things, some of those kinds of things. And so the question was, in this case, if we have as-alias, which says that you don't need to load set, and as, which says that you do need to load set, what should happen? So, and what was happening was that it wasn't loading. So that's being demonstrated here. But we wanted to change that so that it was going to load in this case. And I don't know that I want to pull up load and really go through all the gory bits of it, but load and require and use all end up in this method called load-lib inside Clojure core. And it takes a bunch of different flags and features. And some of these are specific to being called through use. Some of them are specific to being called through require. The conceptual model here of what's happening, though, is that if verbose flag is set, then we want to turn on logging. That's a useful feature. If we need to figure out how we want to load the namespace in question, we can choose to not load. We can choose to check whether it is already loaded, and otherwise, and if it is, then not load. We can choose to reload it, regardless of whether it's already been loaded, but not reload its transitive dependencies. Or we can choose to do reload all, which says definitely reload this thing and all of its transitive dependencies. So there's a bunch of different options there on how much loading should happen. And the change we made is in this sort of area here of if the namespace is not yet loaded and and at least one of user as is in there, then we should load. And then there's some aliasing support, and that was sort of, we've got this sort of two cases now. That was the change in alpha 2 affected this part of it, and whether or not we want to do refers or not, which are also in here. So there's a lot of stuff inside this. It's a pretty critical function. It was fairly daunting to get to the point of comfort that I was actually thinking about all the ways this function is called. Because there are multiple different paths into this code, and there are combinations of flags that are commonly called, and some that can be called but are uncommon. So there are a lot of cases, and I spent a lot of time thinking to be able to write this list here before I even started working on trying to change it. And I ended up changing the implementation of the function more than I had in the original version. I undid a bunch of the changes that I'd done in alpha 2 and changed the way the method was implemented to some degree to closer match to this conceptual model, which I think really matches the meaning of it. So it took quite a while to write this. I'm still, I would say, not 100% sure that the semantics are what we want for every combination of cases. So it would not surprise me if we came back and tweaked this again, but I think at that point it would be tweaking the new structure, which would be easier than tweaking the old structure. The cases I'm talking about are weird corner cases, not normal cases. But
yeah, and looking and having gone through this and to screen it, your work in the ticket was really helpful in figuring out what was happening in the change, and all of the conditional logic happening in that in the NS macro is, I really feel like is something that could benefit from maybe a teeny tiny production rule system just for just for NS.
Yep. Well, and it's interesting in that like linters have that in it, right? Linters have built their own conceptual models of these things from the outside.
Yep.
So I think that's kind of interesting in that it's similar to how like in our brains we build up a model of how other humans respond to us, right? And what that is a really bad copy of that person's brain inside your own brain, right? I don't know. That's just weird to think about to me. But getting all metaphysical on you. Let's see, 2677. So this is one that I probably spent the most time on since the last alpha. And it was really spun off this 2674, which I'll open briefly. And so this was done. So when we released alpha 3 with the new clojure.java.browse stuff, there were quickly questions about whether or not it should really be clojure.math and something that should be made portable to ClojureScript. And that was intentionally not a goal of the original work, but it's a fair question. And so my question was, is that possible? Is it possible to make, a clojure.math in clojure script that is close enough that we would be happy with it as a portable target. And so Paula Guerin went off and tried to answer that question, and she's done a ton of work on it, and I'm really thankful to her for doing that, and for the others that have been out there helping her. Matt, Mike Fikes, and David Nolan, and other people have helped out a bit with some of that work, and so I'm thankful for all that. And the broad answer was yes, it is possible to do this. And so in Alpha 3, one of the things we did was to rename this namespace to clojure.math. So that makes it sort of easier for the renaming logic that's in Clojure script to automatically work with that. And this, I think, will ultimately allow people to write math stuff in either Clojure or Clojure script portably without needing, conditionals and CLJC files and things like that. So good stuff. It's a good result. But one of the things she found while she was doing this work was that she was getting occasionally getting different results for calls to some of the new math methods. And that seemed like a bad thing. So that was the symptom as described to us. And so the reason why that's happening is that math4 mod is a function that, in this particular example, is a function that has both float and double implementations, or int and long implementations. Right? Yeah. This one's an int and long. So and because there are two targets, it was being inlined as a reflective call. And it turns out that the reflector relies on the choice made by the reflector, which is going to be a runtime call, will be based on the methods that are returned from Java reflection. And that set of methods is not deterministically ordered. And so there are several problems here. So when you get down into those weeds, it's a problem that that's non-deterministic, because you end up with cases where you get different answers. So, but you get at different answers because there's actually a narrowing conversion happening from long to int, which actually removes precision. It ends up giving you, in this case, it's like underflow or overflow or something like that on long to int. And so you end up with a different number going into the call and a different bad result coming out. So there are problems here with narrowing conversions, of which there are a number of old tickets, not all correctly identifying the problem, but that's what the problem is. There are problems with reflector non-determinism, but we really focused on the first problem, which is that it was reflective at all. So that's the first problem. So I spun off this ticket, and we've renamed it a bunch of times until Rich was happy that this was actually capturing what the problem was, which is that there are two implementations of every one of these math functions. There's an inline implementation and a method body. It's called for higher order functions. And so the normal function body, we were using type hints to unambiguously select a single call of the overloads. So they were not reflective. In the inline, we were not doing that. And so the inline was reflective. And so the question was, how can we make those inlines not reflective? So, and because reasons, you can't type in. Just because of how it's applied in the compiler, you can't supply a type hint on the function argument in this case. So some options that we looked at, well, the first option was fix the reflector, but this is not a good problem because you've still made it reflective. It's still going to be way slower than the other one. That's not what we want. We don't want reflection. So one is really a non-alternative. We looked at introducing coercions to the inline calls, which I'll talk about, come back to, because that's what we ended up doing. we looked at another option would be to add new internal methods inside numbers or someplace else that basically did the narrowing. So make them non-ambiguous so that it didn't matter what we called them with, they would automatically go through coercions to call the narrower method. That definitely worked. I implemented it. There's a patch here that does that. And in some ways it's pretty clean. And I think it's actually probably the fastest of these options, although it's hard to tell. It's probably a wash with the coercions one. The downside is that you would be adding 16 of these methods that serve no purpose other than to narrow your overload target. And because we would be generating bytecode that called these methods, we would need to maintain those methods in perpetuity for compatibility. Yep. So it was creating a maintenance burden for the future, the long future. So it's definitely not great. And then we also spent some time blue skying about ways to specify a reflective call that embedded type information so that we could specify the exact reflective overload that we wanted to call. And I think that idea is not dead. It is, it exists. We might act on it at some point in the future. So that's still a future possible thing to do. So that was kind of fun to go think about that as another option. But what we ended up doing was basically introducing coercions. And do I have it? So basically it looks like this, is that in the inline call that we coerce to the correct primitive type. And when you then select when the compiler selects the overload for this one, it sees only the known primitive output types of the coercions, and it will always select the call that we want. There are actually some clojure intrinsics. We talked about Java intrinsics earlier. There are some clojure intrinsics that look for things like long-to-long conversions and replace them with no op in the bytecode. And so there's actually effectively no cost to doing this in the case where you have the right type. In the case where you have the wrong type, you still need to do the coercion. And so the big insight here is that this is basically exactly what is happening in the case where you do a method and you call something with the right coercion. The coercion is happening on the call to increment exact based on the type hints you've provided. So you end up with the same effective code through a different route. So I don't know if that all makes sense or not, but so I initially wrote the clojure Java math namespace using a generator. So I wrote some code that generates all of the clojure stuff, the clojure implementation for every math method. We ended up then going through and manually rewriting the docstrings to be clojure specific and doing a few other changes in there. But once we had decided to do this with the coercion, we said, well, we should probably go back and rerun the generator, because we actually found at least one case where we had introduced a bug in a function name. And there were some things like that had happened. So I went back to the generator. So I used clojure. So I used clojure to extract all the docstrings that we had manually written, and I put that map inside the generator so I could recover them. And same thing with argument names and a few other things that we needed. So I recovered the manual work and put it fed it back into the generator basically. And then the generator is actually included in this patch and is actually checked into the clojure repo now. So if you want to go look at it, it's out there. It's not intended to be particularly generic or useful code, but it's under the CodeGen directory is the generator that was used to generate the version of clojure.math that is currently checked into the repo. So if we need to make significant changes to this in the future, we'll do that. And it's not under my source roots here. So it's angry about things, but you know, it's, I don't know, 100 lines of Clojure code that's doing that. And then we had a few other bugs that were out there, like Java doc, just bugs in the Java doc, those manually written doc strings and some other things. And so I fixed those all as part of this generator stuff. All right. That was a fun one. Probably go through these last few pretty quickly.
Yeah.
This clojure.test one is something I think somebody pinged me about because they ran into it. It's not really a big deal, but down inside the guts of clojure.test test reporting, there's an actual value that is not properly coded. It's just a plain bug in the code that's been there for many years. So what was really useful is that there was a better test report. There was a better repro, I think, in whoever forwarded this to me. And that helped make it a lot easier to understand, reproduce, test, and check. So the actual check, I think, is a 1-character change that just quotes in one place where it should be quoting. So simple change, but it was a matter of having the right repro that made it really clear what the problem was and how to test it. This 2493 is one that's been out there for a while, and it actually comes up at the end of the Clojure script quick start for some Linux systems with some browsers. So it will launch the thing and then it waits for a result that we don't care about. Is that right, Fogus?
Yeah, basically, it'll launch a sub process and wait for a return, and the return never comes on some systems and some browsers. And this patch branched out and now implemented a new way for browse URL to throw away those the channels for the sub process and just return immediately.
Right. So it's kind of a weird little, again, a weird little rabbit hole that most people never look at, never worry about, never think about. So this XXE thing is kind of interesting. There's clojure.xml is a namespace that is really old and doesn't do too much. In most cases, people are better served by using the data.xml lib. But one thing that has come up, and I was pinged about this by our new bank security people as well, is that it processes XXE XML external entities by default. And so this is kind of a repro here that lets you use, if you open an XML, if you parse an XML document that has an external entity that happens to look at a local file, it can leak that stuff out into the public. So this is not a feature that most people ever use or rely on. And so what I ended up doing was basically this is just I broke out this helper function sax parser. I created a new function, disable external entities, that basically decorates a sax parser to turn off that feature. I left the existing start parse -sax, and I created a new start parse -sax-safe that uses this disable external entities thing. And I made that the default under clojure.xml/parse, which is what people generally call. So basically, we now turn off that feature by default when you call this, when you call the XML parse method. But if you need to recover that, you can pass start parse -sax as an extra option at the end here, which that was something that was already supported, but not really well documented or used by anybody. So I didn't change anything about the the public API here. I just broke out some tools that you could use if you want to recover the old behavior or not.
Alex, how do you know when somebody's using NixOS?
How do I know?
Don't worry, they'll tell you.
Oh, yes, there you go. Gotcha. So that was a good one. And then the only other thing here was just updating all the, updating all the deps to the newest versions. In particular, test.check has an abs method. And so I released a new version of test.check that refer clojure excludes that. So it doesn't warn. And so when we build clojure itself, we don't get that warning. And then also spec.alpha includes that. And I think the test generative change was just stamping it as 1.0, so it's no big deal. But there you go. That's alpha 4. As far as what we're doing after this, there are some remaining tickets still in the 1.11 bucket. I'm not sure how many of those will make it through all these gates and hoops to get into a release, but hopefully a few of them will. And we might have some other minor feature changes still to come. So we're still in alphas officially, but well, thank you, Fogus. Thank you, Ghadi, for joining us. Hopefully we'll put this out there and see if anybody cares about it or not. So give us your feedback. If you made it to the end, you get a cookie. That was a long thing. So, all right. See you guys.
Yeah.